Now example 11.31. Crystal diffraction experiments can be performed using X-rays or electrons accelerated through appropriate voltage. Which probe has greater energy? For quantitative comparison, take the wavelength of the probe equal to 1 angstrom, which is of the order of interatomic spacing in the lattice, mass of electron that is given to you. Now, lambda, that is 1 angstrom, means 10 raised to minus 10 meter. So, energy of X-rays photons, that is E equal to hc upon lambda. Substitute the value of h, c and lambda, then solve it. You will get energy in terms of joule. Then divide it by 1.6 into 10 raised to minus 19. અહીંયા 10 ની જગ્યાએ 19 કરી નાખજો. So you will get energy in terms of electron volt. Then if for electron we take the lambda that is 10 raised to minus 10 meter, then lambda that is h upon mv. So we can write mv that is h upon lambda, or simply we can write p that is h upon lambda. Okay. Now energy of electron, that is p square by 2m. So here from this particular equation, mv that is h upon lambda means p that is h upon lambda. Substitute the value of h and lambda, you will get momentum. Then substitute the value of momentum here, take square of it, 2 into mass of electron, and you will get energy in terms of joule. Then divide it by 1.6 into 10 raised to minus 19. You will get energy in terms of electron volt. So here energy of X-ray photons, that is large compared to energy of electron. Clear to all of you? Then after 11.32, A. Obtain the Broglie wavelength of a neutron of kinetic energy 150 electron volt. An electron beam of this energy is suitable for crystal diffraction experiments. Would a neutron beam of the same energy be equally suitable? Explain. Mass of neutron, that is 1.675 into 10 raised to minus 27 kilogram. B. Obtain the Broglie wavelength associated with thermal neutrons at room temperature 27 degrees Celsius. Hence explain why a fast neutron beam needs to be thermalized with environment before it can be used for neutron diffraction experiment. A. Now see kinetic energy, that is 150 electron volts. So that is 150 into 1.6 into 10 raised to minus 19 joule. Okay. Now lambda, that is h by p. But previously we discussed momentum p, that is under root 2mk. So mass of neutron, kinetic energy of neutron. Substitute the values of h, mass of neutron, and this value of the kinetic energy, then solve it. You will get lambda, that is 2.33 into 10 raised to minus 12 meter, or you can write that is 2.33 into 10 raised to minus 2 angstrom. But this particular wavelength obtained here, that is very much less than the interatomic spacing. It implies that these particular neutrons are not suitable for crystal diffraction experiment, because if the spacing that is more compared to this lambda, then these neutrons will pass through that particular crystal without interacting with the constituent atoms. So diffraction pattern will not be obtained. Then B. Temperature given to you, that is 27 degrees Celsius, that is 300 Kelvin. Now we have the equation lambda, that is h upon under root 2 mass of neutron, kinetic energy of neutron. But at temperature T, the kinetic energy of the particle, that is given by 3 by 2 kBt. So here if we substitute Kn, that is 3 by 2 kBt, then 2 cancelled. So lambda equal to h upon under root 3 Mn Kb into T. Okay. Again, if we substitute value of H, Mn, Kb and T, we'll get the answer 1.45 into 10 raised to minus 10 meter. That is 1.45 angstrom. And this particular wavelength obtained, that is of the order of interatomic spacing. So this one is suitable for diffraction experiment. So here from this one we can understand this thing. If the fast neutrons are there, then the wavelength will be less, right? So we have to thermalize those neutrons, and then after we can use it for the diffraction pattern. Clear? Chalo, 11.33. An electron microscope uses electrons accelerated by a voltage of 50 kilovolt. Determine the Broglie wavelength associated with the electrons. If other factors such as numerical aperture, etc., are taken to be roughly the same, how does the resolving power of an electron microscope compare with that of an optical microscope, which uses yellow light? Okay. Now see, here the voltage with which electrons are accelerated, that is 50 kilovolt, that is 50 into 10 raised to 3 volt. Now lambda of electron, that is h upon under root 2m into kinetic energy. But when electron is accelerated with the potential difference of v volt, then kinetic energy gained by it, that is ev. એટલે અહીંયા આપણે kinetic energy ની જગ્યાએ ev લખ્યું. Now if we substitute the value of h, mass of electron, charge of electron and voltage given to you, that is 50 into 10 raised to 3, and then after if you solve it, you will get answer 5.5 into 10 raised to minus 12 meter. Okay. Now lambda for yellow light, that is 5.9 into 10 raised to minus 7 meter. Now resolving power proportional to 1 upon lambda. So here we have to compare the resolving power of electron microscope and optical microscope. So resolving power of electron microscope divided by resolving power of optical microscope. Now resolving power inversely proportional to lambda. So we can write this is equal to lambda yellow upon lambda electron. So that is 5.9 into 10 raised to minus 7 divided by 5.5 into 10 raised to minus 12. So this is nearly of the order of 10 raised to 5. It implies that the resolving power of electron microscope, that is approximately 10 raised to 5 times more than that of optical microscope. Clear to all of you? 11.34. The wavelength of a probe is roughly a measure of the size of structure that it can probe in some detail. The quark structure of protons and neutrons appears at the minute length scale of 10 raised to minus 15 meter or less. This structure was first probed in early 1970s using high energy electron beam produced by a linear accelerator at Stanford, USA. Guess what might have been the order of energy of these electron beams. Okay. Now see, here this particular appears at the length scale of 10 raised to minus 15 meter. એટલે આપણે wavelength lambda જે છે એ 10 raised to minus 15 મીટરના ઓર્ડરની જ લેવી પડે. Now momentum of electron, that is h by lambda. So substitute the value of h, lambda, that we have to take of the order of 10 raised to minus 15 and you will get the momentum. Now rest mass energy of electron as per equation E equal to mc square, we can write m0 into c square, and that is 0.511 MeV, that is given to you. So 0.511 into 10 raised to 6 into 1.6 into 10 raised to minus 19, this much joule. Then after we can use the relativistic formula for the energy of electron, and that formula you have to remember, E, that is equal to under root C square P square plus M0 square C4. So M0 C square, that is this one. So this is nothing but the square of it. So directly you can substitute this particular value and then take square of it. And here substitute value of C and P which we calculated, then you will get the energy. Okay. So here second term showing rest mass energy, that is this one, negligible one. Okay. When you solve this one, you will get the energy, that is this much BeV. 11.35. Find the typical de Broglie wavelength associated with He atom in helium gas at room temperature 27 degrees Celsius and 1 atmospheric pressure, and compare it with the mean separation between two atoms under this condition. Now temperature, that is 27 degrees Celsius, that is 300 Kelvin. Now lambda, that is H upon under root 2mk. Now kinetic energy at temperature T, that is 3 by 2 kBt. So we'll get lambda, that is H upon under root 3 mass of He atom, Kb Boltzmann constant, and temperature T. All are given to you. Substitute all the values, then you will get lambda. Now mean separation between He atom, that is molecular volume upon Avogadro number raised to 1/3. So for 1 mole in standard 11th, we discussed this equation, PV equal to RT. So we can write PV equal to NKBT. Now, V by N, that is equal to KBT by P. So substitute in this particular equation molecular volume, that is V, and Avogadro number N. So that is KBT by P whole raised to 1/3. Now substitute the value of KB. Temperature, that we have to take 300 Kelvin, and 1 atmospheric pressure 1.01 into 10 raised to 5 Newton per meter square, and then you will get the mean separation R. Clear? 11.36. Compute the typical de Broglie wavelength of an electron in a metal at 27 degrees Celsius and compare it with the mean separation between two electrons in a metal which is given to be about 2 into 10 raised to minus 10 meter. Very simple thing. Take temperature 300 Kelvin, mean separation between two electrons, that is given to you. Now calculate lambda, that is H upon under root 2 me kBt. Substitute all these values and you will get lambda. Then take the ratio of separation in lambda. You can get the comparison. Clear? Now example 11.37, that is purely theoretical one. A. Quarks inside the protons and neutrons are thought to carry fractional charge plus 2 by 3 e and minus 1/3 e. Why do they not show up in Millikan's oil drop experiment? Because these quarks are strongly bounded under the effect of nuclear forces, and therefore in Millikan's oil drop experiment these particles are not separated. Clear? What is so special about the combination E by M? Why do we not simply talk of E and M separately? Because if we think about the motion of electron inside electrical magnetic field, then see the energy gained by electron under the effect of potential difference of V volt, that is EV equal to half mv square. So in this equation E by M appears. Under the effect of electric field, the force EE, that is equal to MA. So again here E by M appears. Then in magnetic field, the force BeV, that is mv square by r. Again here E by m appears. So E by m appears together in all the calculations, and therefore we take it jointly. Then see, why should gases be insulator at ordinary pressure and start conducting at very low pressure? Gases are generally insulator at atmospheric pressure because even if they are ionized, their positive and negative ions are close together, right? And they form neutral atoms. But at low pressure, the separation that is too much large. So ionized gas at low temperature, that becomes conductor. Clear? So that will be conducting medium. D. Every metal has a definite work function. Why do all photoelectrons not come out with the same energy of incident radiation is monochromatic light? Why is there an energy distribution of photoelectrons? So you all are aware about the structure of atom, right? So here in atom, electrons are in different orbits and are bounded with a nucleus with different energy. So very first, the outermost electrons, means which electrons which are in outermost orbit, will be liberated first. And as we think about the electrons which are close to nucleus, are strongly bounded, so they require more and more energy to be free from it. And due to that, all the electrons emitted are not obtained with the same energy. Clear? Then the energy and momentum of an electron are related to the frequency and wavelength of the associated matter wave by the relation E equal to h nu and momentum P equal to h by lambda. But while the value of is physically significant, the value of V, and therefore the value of phase speed V, has no physical significance. Why? So the absolute value of energy has no significance except as an additive constant. Put with momentum, it is not so. Similarly, for matter waves, frequency has no direct physical meaning, but wavelength is physically significant. And the phase speed, V lambda, that is, sorry, nu lambda, that is V, has no significance, but group speed has significance physically. This particular concept actually, that is out of your scope of group speed and all this thing, because that is of quantum mechanics. So just you have to read it. That's it. Clear to all of you? And now the chapter is completed.